Hello everybody and welcome to this presentation about the detection of antibiotics with molecularly imprinted polymers. In this presentation we will mainly focus on the theoretical understanding of detection mechanisms using EIS and molecular dynamics. The sensors we want to conceive already have a practical application, which is the fight against antimicrobial resistance. This phenomenon comes from a primary infection that's inadequately treated and left some bacterial proliferate and mutate, and that's the phenomenon of antimicrobial resistance. To fight this problem, we can just use a simple solution, which is to limit the amount of antibiotics we use. But in some fields, we can't control the antibiotics we consume. And for example, in the agri-food industry, animals are fed with some antibiotics to fight their own disease. And this quantity might be found back in our food. So we must control this. And we will focus on the case of penicillin G in milk, for which European Union fixed an MRL of 4 ppb in milk. In order to fulfill our project requirements, we need to conceive sensors that consume as few energy as possible. To do so, we will perform conductivity measurement where the sensitive layer is simply deposited between two gold electrodes, and the sensitive layer will see its resistance modified by the presence or the absence of the analyte, and that will be measured by an actual transduction systems. So the material we want to use for the sensitive layer should fulfill some requirements too, and so it should be a semiconductor at least. It should be sensitive to the target molecule, easily processable, and allowing, so as I said, the low energy measurements. And the most convenient materials for this measurement will be the conducting polymers. Polymers are generally considered as insulators. In terms of conducting properties, materials are generally separated in three main groups: the insulators, the semiconductors, and the metals, depending on their band gap, which is the energy barrier between the valence band and the conduction band. For the case of polymers, there are no crystalline structure, so normally they shouldn't have a valence band or conduction band. But some special polymers, called conjugated polymers, exhibit an alternation of single and double bonds, which on a long chain will lead to a stack of p orbitals, which will generate a valence band and a conduction band as in crystal materials. And the main interest in conducting polymers is their doping possibilities. This doping allows to significantly increase the polymer conductivity, but also to modify other properties like optical properties, and to give us a really sensitive material. The point is that those materials are really sensitive, but unluckily their selectivity is quite low. To solve this selectivity issue, we can use what's called a molecularly imprinted polymer. This polymer allows to do the specific recognition of the molecule we want to detect, and it's quite easy to implement, as we just have to put together functional monomers with the target molecule, also called template, to do an assembly around which we will do the polymerization, and then just remove the template molecule to get an unoccupied site able to do the detection later. This technique allows to significantly increase the selectivity and present another advantage, which is the fact that it's highly adaptable, as more or less we just need to change the template to get another MIP sensitive to another kind of specific molecule. In our case, we choose to work with pyrrole as cross-linker and with pyrrole carboxylic acid as functional monomer, and with the template, which is penicillin G, of course. And to get our MIP, we just need to bring together the penicillin G with the functional monomers, do a little pH modification and a little temperature adjustment, and then we add our oxidant and get the polymerization around this assembly. And with just an immersion in an extraction solution, we get the unoccupied site that we want, able to do the detection later with the same molecule. And here on the left, you can see what looks like one of our sensors before the deposit and after the deposit. To ensure that we have good imprinting site after our polymerization, we performed molecular dynamics analysis thanks to the Material Studio program. And this program allows us to put together in a box all the molecules that are supposed to react during our polymerization. And here, for example, we put 2000 molecules of water and 15 molecules of pyrrole, 7 molecules of pyrrole carboxylic acid, and all of this for 1 molecule of PNG, which is quite similar to some of our pre-polymerization solution. Here, the molecules are set in the box randomly without taking into account the interaction between any of those molecules, so it will have to be done. To ensure that we have a good homogenization, with Material Studio, the simplest way is to perform an increase of the temperature with an open system where we don't control the pressure. And here it's what it's done with an increase of the temperature up to 500 Kelvin to ensure that the molecules are free to move around and homogenize the solution. After a few times at this high temperature condition, it's time to get back to ambient conditions, and which is 300 Kelvin and the atmospheric pressure. And doing this, we can see that the template, so the penicillin G, is progressively surrounded by the functional monomers and the cross-linkers to form the assembly that we expect from this pre-polymerization solution. If we take a closer look to our system, we can see the solvatation shelf of the penicillin G. And while removing the water, you can see that the assembly we wanted at the first time is well present. And here we see that the PNG is surrounded by either the functional monomers and the cross-linkers. With the software, we can even calculate the presence and the energy of the hydrogen bonds, here represented in a blue dot line. The analysis of this energy allows us to define for lots of composition which one will be the best and will give the assembly with the lowest energy, and so the most probable assembly before the polymerization. So for one PNG molecule, we tested a lot of different composition, and we get already the conclusion that the best polymerization solution should be between 11 and 15 molecule of pyrrole for one PNG molecule, and between 4 and 10 molecule of pyrrole carboxylic acid for one PNG molecule. For the records, actually, the experimentation and the literature reference 11 pyrrole molecule for one PNG molecule and 4 pyrrole carboxylic acid molecules for one PNG molecule. And we even tried other solvents, as here acetonitrile, but those solvents didn't give sufficiently good results. And even in this case, so for the same composition as presented before, you can clearly see that around the template, there is no functional monomers or cross-linkers, and if the polymerization takes place in this system, it will certainly not be the polymerization that will give molecularly imprinted polymer. So now that we know that our MIP presents a good imprinting site, we may perform the detection itself. And to do so, we use the method that I spoke about before, the electrochemical impedance spectroscopy. It consists of the application of an alternative current in a 3-electrode system at variable frequency, and this allows us to point out the different kind of interfacial reaction. In our case, in this system, we connected the 2 electrodes of our sensors, the interdigitated electrodes, to the counter and the working electrodes. And we can observe on the graphs, which are represented usually under the Nyquist diagrams and the Bode diagrams, which can be magnitude or phase diagrams. We can observe some kind of curves that we can fit by modelization. And this fitting might let us know what kind of physical phenomenon occurs in our system. And for example, here on the right of the slide, you can see the example of a time constant, which is represented by resistance and capacitance in parallel, which give the curves that are presented here. And for the remind, on the Nyquist diagram, you can see the imaginary part on the y-axis and the real part on the x-axis, while on the Bohr diagram, you can have both the magnitude and the phase on the y-axis, while having the frequency on the x-axis. So this system gives us the results presented here. They are presented under the both diagrams, with the phase above and the magnitude under. You can see for each of these graphs the evolution of each data curves. Each data curve being the corresponding addition of 12.5 ppb. So data 1 being 0 ppb, data 2 12.5 ppb, etc. On the left, you can see the MIP answers. That are the answers furnished by the MIP sensors that we presented before. And on the right, you can see the NIP answers. What are the NIPs? The NIPs are the non-imprinted polymer. And the non-imprinted polymer are exactly the same polymer as the MIP, except that during the polymerization step, we don't put the template in the solution. And doing that, we don't get the imprinting site that we normally have with the MIP. And the interest of comparing the MIP and the NIP is to point out the interest of this imprinting site. And here we can clearly see that for some frequency, we have a better variation for the MIP than the NIP. And we can put this information into a graph where we report the response versus the concentration, and we can clearly see that the MIP is better than the NIP. And even in the magnitude graph, we can even see that the MIP answers is quite direct, as we get an answer as soon as we do an addition in the solution. But in the NIP, it's not the case. We only get the first answer at 37.5 ppb. So regarding these results, we can clearly see and say that the MIPS provide good answers and better answers than the non-imprinted polymer. Now that we have our results, the idea is to use what we call impedance spectroscopy models. So in particular, we will try to develop an electric equivalence circuit whose elements parameters are equivalent to physical properties of the real system. So what does it mean? It means that at first we will try to consider the different paths a charge can use to go from an electrode to the other. So at first, an easy one is the first path, which means that the charge go from one electrode to the other, going through the polymer, which should not be too much resistant. In the second case, the charge will prefer to pass near the interface between the solution and the polymer, because this interface might be less resistive and offer a better way to the other electrodes. And the third way is the way where the polymer is sufficiently resistive to make the path easiest to go through the PBS solution to get from one electrode to the other. In particular, to develop our system, we get something like this with some different components in it. So we have capacitance and resistance. So here, capacitance of double layer and resistance of charge transfer. And both of these elements, for example, represent what we called before a time constant. With that, we have classical resistance, so resistance of solution for the PBS solution, and the polymer resistance for the R polym 1. We have also a modulus that takes into account the diffusion modulus, so it's called the Wahlberg modulus. And we have some elements that are mathematical tricks to fit our curves. So here a CPE, it's a constant phase element. So it's similar to a capacitance, but with parts of resistance. Now that we have our electric equivalent circuit, we can try to fit our experimental results. And that's what we try to do here with the response provided by one of our sensors at 0 ppb per Ng concentration. And as we can see on those graphs, we can't barely distinguish the two graphs from the fitting and the experimental results, which can lead us to the conclusion that this fitting is quite good. But I have to tell you that the electric equivalent circuits that we conceived before have been conceived with these experimental results. So to be sure that our electric equivalent circuit is a general circuit able to fit any results we can obtain, we have to test it on other sensors and on other concentration to be sure that we have still a good fitting capacity. And that's what we try to do here with different response obtained for 3 different sensors synthesized in 3 different pH conditions, still at 0 ppb of Ng concentration. And we can see on the magnitude graph that we have quite a good fitting of the experimental curves obtained by our electric equivalent circuit. However, we have to note that the fitting are not as good on the phase fitting diagram. In particular, the sensors synthesized at pH 3.2 doesn't exhibit a maximum at a low frequency, which is quite complicated to fit with our model. And here are the results that I showed before for one sensor at different PNG concentration. The blue curve at 0 ppb, the orange curve at 50 ppb, and the green curve at 100 ppb of PNG. And as you can see, the fitting is quite good on all of these curves. So we can say that our fitting is able to model an evolution and an increase of the concentration in our solution. Now that we know that our electric equivalent circuit is able to model the increase of the PNG concentration in our solution, we have to focus on some of these elements that can help us to better understand the physical phenomena that occurs during the detection step. And to do so, we need to define those parameters. So here they are highlighted in red. So there is the second resistance of charge transfer between the polymer and the solution, and the two diffusion coefficients in the polymer. But in those elements are hidden some parameters, and so parameters at plural, because for example, for the finite length Warburg, there are 3 different parameters that might vary during the detection step. There is the resistive parameter, so the kind of classical resistance. The T parameter that includes the diffusion thickness and the effective diffusion coefficient, and the diffusion parameter that is the mathematical parameter comprised between 0 and 1. And here are presented the evolution of the different parameters with on the left y-axis the diffusion parameters and on the right y-axis the resistive parameter. And from those evolutions we can draw some conclusions. As for example, with the P parameters, we can say that when it gets close to a 0.5 value, we are close to a one-dimension diffusion. In the same order, with the evolution of the T diffusion parameter, we can say that the diffusion thickness is decreasing quite a lot during the detection step. And the last but not least, the evolution of the resistance charge transfer between the polymer and the solution, we can see that there is a lot of increase of the resistance parameter, which can be due to the fact that during its adsorption, the penicillin G prevents the charge to go from the polymer to the solution. To conclude, we can say that we performed a theoretical optimization of the composition of our polymerization solutions, and that we performed the fitting that allowed us to determine the variation of the physical parameters of the sensitive layer during the detection step. But there is still a lot of things to do in this subject. As for example, we can carry on the investigation on the optimization of the polymerization solution. And we can also think about modelizing the extraction phenomenon with Material Studio and do the same for the detection phenomenon. And at last, we want to perform DFT analysis in order to verify if it's possible or not to perform optical measurements. Thanks for your attention and feel free to ask if you have any question.